My question is, if I give you this sequence or this plot, and I say that you have a quantizer, you have an input to your quantizer, which is giving you this sequence as a output. So my question is, we saw this is the discretized or digital sequence which our quantizer gives us as an output, which looks like this. So can you look at this output of the quantizer and comment on how the input would have looked of the quantizer? This is how the output looks. So can you tell me how the input might look by looking at this? So, I mean, you can answer me a yes no question. So what if I draw a line like this and I say that input would somewhat look like this?
Yeah, it
It's
can
like
be.
sinusoidal
Yeah,
Like,
it's sinusoidal.
signal.
so
Yeah, yeah.
you can, you're with me at this point, right?
Yes.
So now like so we saw the quantized output. We said, yeah, okay. So this is the curve of, if basically if this was the curve of the quantized output. So we said that, oh, doing this will probably estimate the input to the quantizer. So this is how the quantizer's input would have looked, right? This is what we said. So what are we technically thinking over here is basically we are averaging the curve, right? So at each and every step, we are averaging the curve and we are taking the average value. And what is the basic assumption we took at this point? I mean, what is the basic assumption we considered while drawing the curve? So in the back of the mind, we said that yes, so if so this is the thing that if we said that the samples are so close, so we are basically drawing a continuous curve like this. So this is the continuous curve, right? But the input to the quantizer is not a continuous signal or continuous time domain signal. It is a discrete or the sampled signal. So it's not a continuous. Just for our sake of convenience, we draw the signal as continuous, looking like a continuous looking line. But they are small samples. They are so close to each other that they are looking as a continuous signal. And then we drive the signal like this. So basically, the very basic understanding or very basic assumption in this case is we consider that there is a lot of oversampling. I mean, the sampling rate is too high. That's what is like if the sampling rate was too low, then this signal we were not like the assumption was wrong then, because if this is the rate, so the samples are too away from each other. So basically the sampling rate is too low. So then we could not I mean we could not write this signal in this way. But if like this is basically the samples are too close to each other that we can draw a continuous curve, so that the basic assumption in the back of our mind was that the sampling rate is too high. So if the frequency of input signal is, let's say, fb, so Nyquist says that we need a sampling frequency which should be greater than 2 times FB, but we are taking such a high sampling frequency that we have a oversampling, and we get a oversampling ratio. So basically, I want you guys to catch me up with this concept or this way of thinking, that first thing, we are able to represent this for the sake of our convenience as a continuous signal, because the samples are so close to each other that we can represent it as a continuous signal. And that's why the samples are very close to each other. So that means we have a very large sampling rate. So that means we have a oversampling. So we assumed oversampling already, and that's how we commented. Okay, then we can comment on this curve that input would look like this. So what this simply means is, if we take two successive samples, let's say we take nth sample in between somewhere. So let's say here is our nth sample, and the next sample, which is n plus 1th sample, they two are very close. So the variance in this curve, or the variance at that position of the curve, is very minimal. That's how we can average it out, right? If the variance was like the n sample was here and the n plus 1 sample was here like this somewhat, so the variance was too high, then we couldn't have had assumed that it is the variance is too low, and then it would have been a greater mathematical problem. But over here, we are basically saying that if we are assuming that we have oversampling, so we are saying that the two successive samples do not have as significant variance in between them. They are somewhat similar. So this is the basic assumption we are taking. So I want to bring you guys to this way of looking at this problem where we are discussing the oversampling ratio. So then I'll share my screen, and I would like to start with this discussion. So this discussion basically says that first thing, please let me know if the screen is visible. I mean, my notes are visible.
Yeah,
Yeah.
it is visible.
Yeah, perfect. So then I would like to start with the idea of oversampling. So I would say that in the initial videos of sampling, as I discussed earlier, we saw the advantage of oversampling. And now let's jump into another oversampling advantage. So the thing is, um, can you guys see the screen? I mean, can you guys see the highlighter?
Yeah.
Yes.
Okay, perfect. So then I'd say if the input, so remember all the discussion we had a few minutes back. So if the input is varying very slowly with respect to the sampling rate, basically two consecutive samples are not that much different, or if the signal is highly oversampled, then simply looking at the quantized output, so simply looking at the quantized output, we will be easily able to give much better approximation of the true input or the input signal to the quantizer, as the mean squared error between the quantized output and the true input is basically given by delta square by 12, and this error gives or tells us about the difference between quantization output and the true input. So we have a discrete quantized output, and we had some sinusoidal sequence as an input, and the difference between two is basically our quantization error, and we said that is our quantization noise, and that is basically delta squared by 12. So delta is the step size. So we know that if a signal is oversampled, it cannot vary rapidly from sample to sample. I mean, every successive sample, there is no rapid variation, which means the true signal is predictable. Hence, if we are provided with the information that the signal is oversampled, then just by looking at the quantized curve, we can approximate the true signal, which we already did, right? And that approximated signal, or that approximated input signal, would have very less quantization error. So I'll come to this line. So averaging, so what we did by approximating, so we had this to quantization output, we said, yeah, so this is the curve of the input, somewhat it will look like this. So then what we were basically doing is, at every step we were averaging the value. So basically averaging is done while approximating the true signal from the quantized output. And technically, in technical terms, averaging is nothing but a special case of filtering. So we are filtering out the higher contents, and we are averaging over here. So basically averaging is low pass filtering. So then, given an oversampled signal which is being quantized, the error between our reconstructed signal. So now we have some input at the quantizer, we have this output of the quantizer. And if we smooth out the output of this quantizer, then basically that is something which we have reconstructed as a signal. So the error between our reconstructed signal given the quantized samples and the true signal is provided to us. So basically the error between the reconstructed signal and the original true signal, so basically it can actually made much smaller, which is delta square by 12, right? So we can make much smaller than that error by simply low pass filtering. So what I mean over here is we have an input signal, we have a quantized signal. So error between them is delta square by 12. Now if we have an input signal already, so if we smooth out this quantized signal, so basically if we low pass filter this quantized signal, then whatever we'll get, that will be having very much smaller error than delta square by 12. So it will basically resemble with the input very nicely. So this is what I meant over here. Hence, the aim of quantization is basically from the quantized samples, we have to go and figure out the true input. If we had no other information about the input signal, then we would have quantized the signal with mean squared value of delta square by 12 as error, and that was the end of the story. But however, we have an additional information that the signal, input signal, is a sequence which is highly oversampled. It means that the signal is not drastically changing from sample to sample, and immediately by looking at the quantized output, so basically quantized samples output, we can give a better estimation of the input signal by simply smoothing out the discontinuities, which is in technical terms low pass filtering the quantized output. So also due to the better approximation of true signal, the quantization error mean squared value has reduced. So it's not delta square by 12 anymore. It is very lesser than that. So basically oversampling reduces the quantization error because the difference is basically delta square by 12 and now it is reduced. That was our over like that was basically our quantization error, right? So what is the conclusion? So the conclusion is oversampling reduces the quantization error, but there is a method of doing that. So we have a signal, right, whose in-band frequency or bandwidth is, let's say, FB. So this is a continuous signal. So what we do is, so now Nyquist say that we need to sample it at or more than 2 FB, but we sample it at very high rate. So very greater than 2 FB. So then we can represent our sampling rate. So let's say 2 FB is our Nyquist criteria. So we said that Fs should be greater than 2 FB, but let's say Fs is, I mean, it's the sampling rate, which is Fs. So Fs is nothing but 2 FB time OSR. So this is simple mathematics, like think of it. If input is FB, if sampling rate is Fs, so Fs is nothing but 2 FB times oversampling ratio. So oversampling ratio is nothing but Fs by, I mean, whatever the sampling input was. So basically, we have a sampling at 2 FB times OSR. This is our sampling rate. And after doing oversampling, we do the quantization. So at the quantization output, we have quantized output. And then if we smoothen it out, so we average it out, so we pass it. So at this point, we have a signal which is discrete in time. So it became discrete in time here only. And after that, we quantized. Now we have also discretized it in amplitude. So we have discrete in time, discrete in amplitude, and that's how we say that our signal is now digital. So to filter it out again, low pass filter it, we need a digital low pass filter. So after having this signal as output of quantizer, we pass it through a low pass filter, we smooth it out. So we average it out and then we get the quantized signal, but also low pass filter. So then at this point, we can say that the quantization error was basically the input. So x minus xq, or basically xq minus x, and its root mean square value was the quantization noise, which was delta square by 12. But by smoothing it out, or basically by low pass filtering, the sequence we get now, which is xq of f, will be a lot better approximation of, so it will resemble with X, not the original signal, the sampled one, the sample signal. So X and XQF, so basically X, so I'll erase all the highlights. So X and XQF will be very much similar, and the mean square error between X and XQF will be much smaller than delta square by 12. So this is the benefit of having a oversampling ratio. So let's say then this is what we are talking about. So this is our input, and we have a widely broadly spreaded noise, which we said that it is delta square by 12, and the mean square value of that noise. So if we take this particular case where f in by fs is 19 by 4096, so what do you think, guys? So let's say 19, so round it off as 20. So we have 20 over here, so 20th bin, we have 4096. So round it off by 4000. So then over here, we will have somewhat n by 2, right? So this is somewhat 2000. So we have a record length of 2000, and we have a frequency bin at 20. So what is OSR? So 2000 divided by 20 somewhat, it comes up about 100. So our OSR is 100 in this case. So based on this value, our delta square by 12, or the mean square variance, or the standard deviation of noise, comes out to be 42.98 into 10 to the power minus 4 dBs. So then um, basically, if we we choose a digital filter which is Butterworth, let's say $6 digital filter, forget about the order as of now, let's say it's a brick wall filter. So if we choose a digital filter, so then what happens is, anyway our signal is at lower frequencies, and we choose a filter which is somewhat like this, or let's say we choose a low pass filter. So this is how a low pass filter looks like, right? So then we will only get the quantity of noise, or the density of noise in this filter, and all other noise is filtered out, and our signal remains as it is. So basically, obviously, now the noise density is reduced, so SQNR is reduced. So after filtering, we get a smaller quantization noise, and let's say the quantization noise is white, then the power would go down by a factor of, so by what factor would it go down? So let's say we consider a digital filter which is like this, and its bandwidth we considered as pi by 10. So n by 2, or fs by 2 over here, represents as pi in frequency domain. So let's say we have a filter whose bandwidth is pi by 10. So it was pi, and now we have pi by 10 over here. So the band range is pi by 10. So as fs by 2 corresponds to pi, fs by 20 will correspond to pi by 10. So we had fs by 20, right? So it will correspond to pi by 10. And that's how we say that if the noise, so basically noise density is delta square by 12. And if this delta square by 12 is spreaded over a range of pi, so if we only consider the noise over a range of pi by 10, then it will be delta square by 12 times 1 by 10. So it will be reduced by, go down by a factor of 10. As earlier, noise was going from 0 to pi. Now filtered noise will go from 0 to pi by 10 only. So the remaining noise power is now 1/10 of the original power. So if noise is reducing, then SQNR will obviously increase, right? So I can demonstrate you using a Python code over here. So over here, let's say we have a filter, and I changed some values over here, but let's stick to the original values where the order of our Butterworth filter. So where is the order? Hmm. Let's say the order of Butterworth filter is 6. So then, perfect. So now we have a 3-bit quantizer. We have this widely spreaded noise. We also talked about the peak of the noise. We have talked about this. We have this original signal, input signal, which is lying on the 19th bin. We have n by 2, which is 2024, and sorry, 2048, and we have this quantization noise. But after digitally filtering out, the noise remains only this part. And basically, mean squared error of quantization noise over here is, as we said, 45 something into 10 to the power minus 4. So our approximations are anyway right. So this is how it looks. So now let's come to time domain. So we discussed in frequency domain. So what happens in time domain? So in time domain, clearly, digitally low pass filtering version of the quantized signal and the true input signal has error between them, which is significantly smaller than delta square by 12. So using a green curve, I have represented the input sequence, and using the blue curve, there will be some error over here, but it will be very lesser than the one which we had in the quantized domain. I mean, in the quantized output. So basically what happens to the noise is the amplitude of the noise is significantly reduced, meaning the power of the error is, or the power of the noise is reduced. So I can represent it using this. So if we had this input signal and if we has this quantized signal, so the noise, if this is the noise, then after filtered out, the quantized noise in frequency domain will look like this. But let's not focus on this. The filtered quantized signal will now look like this, which resembles to the original signal very nicely now. So the error between them is obviously very less. And if the error is less, so initially, so this gives us the error or the noise which we had earlier. But after low pass filtering, this is the noise which we are getting. So anyway, the filtered noise or low pass filtered noise is anyway very less. So the SQNR is boosting anyhow. So the moral of the story. So moral of the story is if we are provided with the information that the quantizer is having an oversampled input, then we can increase the effective resolution of the quantizer. Why? So the quantization noise is being reduced, right? So the SQNR will go up. And if SQNR will go up, then we know SQNR equals to 6.02 times N plus 1.6. So if this value is basically going up, is simply meaning that N is going up. So resolution is going up. So just by having oversampling, we can increase the resolution. So we can make the lower resolution ADC look like a higher resolution converter. As we know, if the error goes down by a factor of 4, this means it increases the resolution by 1 bit. So in upcoming concepts, we will see that using oversampling, we can make a 1-bit quantizer look like a 16-bit quantizer. So that's all from my side as of now for this video. Thank you so much.